Radioactive fossils. At first, it can sound a bit far-fetched, but is it? I'm your mental curator, Johnny Hemberger, and this is the HMNS Beyond Bones podcast presented by the Houston Museum of Natural Science. My guest today is our paleontology lab manager, Colin Diggins. Get comfy and relax as we explore the idea of radioactive fossils and much more in this fascinating episode of the HMNS Beyond Bones podcast.
Colin, thank you so much for coming on the Beyond Bones podcast again
My
this
pleasure.
week. Yeah. So there's a very interesting question I want to pose that comes up quite frequently in the comments we get on YouTube and with the podcast in general. Can fossils be radioactive? So let's start there.
Yeah, absolutely. That is a better phrasing. And it's not all fossils, obviously, are radioactive. It really comes down to where they're forming and how, right? So there's a number of different radioactive elements out there that are very present in certain types of minerals and different types of formations, right? So we're sitting here in front of Dipsea, our Diplodocus, which comes out of the Morrison Formation, which is an area that's actually mined for uranium, right?
Wow.
So they look for ores or rocks essentially that bear uranium for enriching for, whether we're talking nuclear weapons or energy or what have you.
Right.
And radioactive minerals can be kind of dangerous at times. But in the whole general Morrison Formation, there is sort of a higher level of uranium just due to sort of what rocks were eroding at the time and being, redeposited as sedimentary rocks, which is the sorts of rocks that you find fossils in. And depending on what sort of minerals are present, especially if they end up kind of getting dissolved in groundwater, they can end up being absorbed by these bones of ancient animals as they turn into fossils, right? So fossilization, which is not really a great term, we tend to prefer something like mineralization, right? Or sort of how something becomes a mineral or turns into stone. When it comes to fossils, I mean, a lot of the time things like bones are actually very naturally porous, or wood is very porous as well. So it's good at soaking up water, and sometimes those minerals can be left behind. And organic structures don't tend to survive very well. So the way that they end up getting surviving as fossils is when they mineralize well, when they absorb a ton of that sort of dissolved mineral from the groundwater, and are converted almost entirely into rock or stone.
Right.
In some cases, depending on how old fossils are, you can still get a bit of like the original mineral component of bone, what's known as apatite, or as a biomineral, right? It's something that the body built. So it's not technically a mineral, since those are just created by nature.
Right.
Not by living things, but by natural erosional forces and that sort of thing.
Right.
But fossils, they can absorb all sorts of different minerals as they're forming. The best ones usually absorb lots of silica. They get very hard. They become like glass. Some of the best petrified wood is often referred to as silicified. It'll polish up beautifully and show you its internal structures and things like that. Cool. But if there are radioactive elements present in the groundwater, they can end up as part of these fossils as well too. So in the Morrison Formation, it's often uranium. And now it is important to note too that these fossils generally are not dangerous, right? While they might be slightly radioactive, it's not at levels that are going to be at a risk to our guests or visitors here at a museum.
Here's a good point. I'm going to prove that point right now. Because of course I have in my pocket a Geiger counter, which happens to be at 0.17 as I'm pulling it out of my pocket. I don't know if the camera will pick that up. That's too close. I'll get a closer shot. But as of now, it's at 0.12. These are not dangerous levels of radiation. The normal background radiation, if you're sitting at your house, if you're driving around in your car, if you're doing anything in life, the normal background radiation in microsieverts is considered between 0.1 and 0.2. Right now, in front of Dipsea, the Diplodocus, it is at 0.12, which is perfectly within the range of safety. It could go even higher. This could go to 0.3, 0.4, and we'd still be just fine. Like you were speaking to, there are some fossils that are more radioactive than others, and I've heard it mentioned, you're fine to work on them, but you wouldn't want to put them under your pillow and sleep with it for years, under your pillow like that, absorbing that radiation over time. There's another consideration you were talking about when we were back in the lab prepping for this, that it's not just about, safety isn't just about, safety with radiation isn't just about, and concerning fossils, isn't just about being around it, but you're doing a lot of grinding, you're doing a lot of work, you're making a lot of particulates. Can you talk to us about being safe around radioactive fossils
Yeah,
in
actually.
preparation?
So, when it comes to preparing these fossils, when you're cleaning them up, removing all the rock around them, again, there's the possibility of some uranium, some radioactive elements in that rock as well, not just in the fossil bones. And we create a lot of dust naturally, since the tools we use are powered by air pressure. They tend to want to blow the dust away from the area that you're working in. So if you're working on rock that might potentially contain radioactive elements, you want a lot more additional containment, right? You want it probably like a air cabinet that you can work in, almost like they do in space, like NASA does, right? But it's going to make sure that it's constantly being suctioned away and vacuumed out, so you're not breathing any of that in and introducing those radioactive elements into your lungs where they could potentially stay for a long period of time.
And you don't want dust particles in your lungs.
In general.
Period.
Yes.
So
Yeah, especially when it's sand and all this silica, it's really terrible for your lungs. So we always use at least some degree of airflow, suction, vacuum to try and keep the areas where we're working in free of the particulates and the dust. But there's just that extra level of concern if there's a possibility of some radioactivity.
Right. So on the extreme end of the spectrum, and by the way, I'll restate. You're safe when you come to the museum. There's no increased radioactivity around here. I've got the Geiger counter right now. It's at 0.08. Still, it's even below what's considered the safe threshold. So don't be scared to come to the museum, see your fossils. Nothing's going to make you glow or grow a third arm. Or the fish in Simpsons with the three eyes in the nuclear waste of the power plant there. So on the extreme end of the spectrum, and what made me think of this question for a podcast is, when someone hears that fossils can be radioactive, there's one wild theory that I've heard that was postulated on a show called Ancient Aliens, apparently, where this is the extreme end of the spectrum, but it's a fun thought, at least, even though it's most likely very not true, is that the age of the dinosaurs, the extinction event wasn't the Chicxulub asteroid, which more on that in a second.
Yep.
But it was actually alien beings surrounding Earth with their spaceships and basically nuking the entire surface of the Earth to get rid of all these pesky dinosaurs to make way for humans. And that's why the dinosaur fossils or any ancient creature's fossils are radioactive, is because the aliens were using nuclear weapons to clear the slate for a higher intelligence, being human beings. Now, I would say that to my knowledge, and possibly to yours, there's not a lot of supportive evidence for that.
No, I wouldn't say there is. The Chicxulub impact, the iridium layer you find at the KT impact, the layer of where you stop finding, the large dinosaurs at least.
Right.
I don't believe that there's any evidence that that's coming from a nuclear bombardment, right? It seems like that's a more natural bombardment, and just in terms of an asteroid impact, it's a rare earth element. It's found a lot more in space, right? But it's not a component of any like nuclear devices, at least that mankind has ever made.
Right.
So it's one that I don't think has ever caught much mainstream support. I would say. And sometimes, fossils can be more radioactive than just the sort of background you'd find in the formation that they're in. But a lot of that has to do, again, with sort of their what's the word I'm looking for here? Their tendency to absorb those minerals from the groundwater at a different rate compared to some of the sediments around them. Sandstone being like very porous probably allows water to flow through it a lot easier. These being porous, they tend, but having much lower porosity and a lot lower permeability, do tend to absorb water, but not and retain it at very different rates. And then that also makes a difference in terms of what sort of minerals they absorb and how long, and whether or not they stay there or are carried away by groundwater too. And it's not something that you find universally. It's not in every formation. It's not across the globe, generally speaking, right? This Jurassic Morrison formation is about 150 million years old. So it's well before that KT extinction about 66 million years ago.
Way before.
Yeah. So it's very separate sorts of extinction events, and that radioactivity isn't sort of a uniform blanket across the globe.
And a lot of when it comes to radioactive fossils, one being radioactive and one being another, I should say one being more radioactive than another, it is purely circumstantial and specific to that fossil circumstances of becoming mineralized. You know,
Yeah.
when you build camps on a river, you're aware of what's upstream of the river. You don't put a dead horse in the water upstream of your camp where you're drawing water, because you're going to draw all the bacteria and all the nasty things that come off of that decaying horse into the population of your camp and everything like that. So it's a similar way, in my mind, you can correct me if I'm wrong, with fossils. It matters where they were over the millions of years that it took them to mineralize. Were there radioactive components leaching into the sediment and leaching into the water when they were becoming mineralized?
Absolutely.
And in the case of a lot of Morrison Formation stuff, at least Dipsy in this case, yeah, there were some radioactive materials in the water, and you can test it. You can see that the fossils are a little bit more radioactive than the background radioactivity. But you can find a fossil, even in I would assume, correct me if I'm wrong, in the Morrison Formation, that its circumstances were different, even just perhaps a few hundred yards away or a mile away. This fossil is not very radioactive compared to this one, which just so happened to have all these circumstances surrounding it to make it more radioactive.
Yeah, there's a whole discipline in paleontology, and some of it applies to other disciplines too, like archaeology, but it's called taphonomy, right? It's the study of basically everything that happens between the animal dying and it being found. It's the whole study of just the conditions of its burial, what sort of circumstances and what sort of conditions it's been subjected to. And that's something you do on a site-by-site basis. It's a very discrete area. You don't try and do that for the entire, Jurassic Morrison Formation or anything like that. It's these conditions, even though they might have all the formation generally formed in sort of similar conditions across that area, every little area is subject to its own little quirks and things like that. I mean, a lot of the time these formations are from river systems, whether they're a meandering river system or a river delta or something like that. And we're talking about, say, like the Hell Creek Formation when T-Rex and that KT extinction, right? And so you have different branches kind of at different times. The sediments get eroded and redeposited, and it could be, the water flows in from a whole bunch of different areas in the catchment basin. So on one side of how these tributaries are flowing into the main streams, you might have different types of rock being eroded, and they're all getting mixed together potentially, but it depends on which branch you end up in, what sort of water you're getting exposed to.
Right.
So I know even in archaeology, when studying the bones of people, we can measure things like stable oxygen isotopes. They're not radioactive at all, but those proportions can tell you basically, it shows up in different proportions based on the water the person was drinking and gets incorporated into their bones at different rates, even as a living animal. So it's really kind of amazing sometimes, just one side of a mountain range or something like that can have a huge difference on what sort of minerals are present in your groundwater and things like that.
There's a spring that you mentioned that it was in Colorado recently. Why am I blanking? Cascade, Colorado. And there's a town nearby and blanking on the name of. I'll put in the podcast notes, or if this winds up on YouTube, which it will, I'll put it on the screen or something. There's groundwater, and it says, you are free to drink this natural spring water. Please enjoy this natural spring water. But the sign says, but enjoy it as a novelty. You don't want to drink this every single day, because if you drink it every single day, technically you can get a buildup. I think it was manganese. I want to say it was manganese. And high doses over a prolonged period of time can cause birth defects and different ailments and things like that. So the groundwater, this is not some ancient concept. This is the idea of minerals being in the water that are radioactive than others, more radioactive, less radioactive. But it's the same processes are going on today.
Absolutely.
I think a lot of people think about fossilization and things like this is something that happened millions of years ago. This is a process that's happening right now. So if something is fossilizing, and probably it is, in Cascade, Colorado, around these natural springs and with the creeks going out and the snow melt and everything going on, yeah, those fossils will be imbued with those chemicals, those elements, those isotopes, possibly being radioactive, possibly being, if there's a lot of manganese in the water that humans need to worry about, then there might be a lot of traces of manganese in the fossils that form around that area. That is taphonomy, am I saying that right?
Yeah. Mm-hmm.
That's a very fascinating to think about.
It is, absolutely. And I get kind of lost thinking about it all the time, especially, again, with my focus in Ice Age, sort of Pleistocene animals, and the fact that we in Houston sit on those Ice Age sediments. The youngest of those fossils are, 10,000, 11,500 years old, something like that. And a lot of them are not very well mineralized. I mean, there's probably not much of the collagen, sort of the very organic, component of bones. Is the stuff that makes like bone broth so nice.
Right.
But there is still a lot, all of the original apatite, all the mineral components of the bones still there. And then at the same time, things that are probably of a similar age, or maybe as old as 2.5 million years old, can be incredibly well mineralized. They're beginning to silicify, and they're hard, and they're like glass, and they're very fragile, but they also, are very hard too. And that's something that it's a very dynamic process too, which is something we don't tend to think about a lot. We tend to think of it as being one line, right, from being the original bone to becoming a fossil, but there can be periods where bones are mineralizing or then demineralizing if the water becomes acidic, and it can leach minerals from the bones and begin to destroy them gradually, which might be one of the things that we're looking at with the material we work in our lab that's Permian, that's 280 plus million years old. Right. It's undergone a really long taphonomic history. It may have undergone some really complex processes where it mineralized partially, then demineralized, remineralized. It undergoes some distortion sometimes from just all the pressure of the sediment on top, where it tends to, kind of break and shear and distort a little bit. And so unpicking all that distortion is another really difficult thing to try and imagine, or sort of bring these bones back to looking what they looked like when they were originally getting buried.
Right. You're making me think of, and it's a small tangent, a steak. I got a ribeye and a New York strip yesterday. And my wife was asking me, do you want me to put these in the freezer? Should I leave them out? If you're going to cook them, whatever. So there have been times, anybody watching this or listening to this has probably been there, of changing your mind about whether or not you want to cook a steak tonight. So it's out of the freezer, back into the freezer, out of the freezer, back into the freezer. And that's another thing, temperature swings in fossils and fissures and cracks and temperature change.
Yeah,
things like
especially in those areas where you've got groundwater freezing. If they're near the surface, that expansion and contraction can cause fossils to gradually get destroyed, which is why we try to get to them as they're getting eroded and getting exposed, because sitting out on the surface can be really terrible for these fossils. But the same things can be happening just 6 inches, 8 inches underneath the surface too. So
that steak that's talking about, it changed. It changes if you're doing that all the time, freezing and unfreezing, freezing and unfreezing, freezing and unfreezing, bringing room temperature and then back to freezing it. That steak at the end of that process is not going to taste the same
as it was when it was like fresh from the cow.
Defrosted once and then cooked correctly and everything like that. You're talking about finding fossils, especially, and correct me if I'm wrong, you're the expert, Ice Age material. We were talking about mammoth bones, specific mastodons and things from around 10,000 years ago. We have a pit in Texas, and there's one up in South Dakota. They're around.
Yeah, there's a bunch of really great mammoth sites, mastodon sites, depending. Yeah.
And you're talking about like 6 inches under I mean, things can be right there. And as soon as I've heard, because I have not dug for Ice Age material myself. I have gone to the Morrison Formation. I've been very lucky to be able to dig for
it's kind of amazing.
Barosaurs and allosaurs. I mean, it's humbling. Like it is such a cool experience. Now those bones, those fossils are pretty, we got to treat them with care, but they are, for the most part, from what I experienced, pretty solid.
Pretty stable is usually the word we use. They're well mineralized.
Stable, exactly. Yeah. Versus a mammoth bone from 10,000 years ago, 12,000 years ago, much closer to the surface. I've heard that as soon as you brush some material off of it, you can see with your eye fissures starting to form. As soon as it meets the humidity or the atmosphere or the temperature, anything, it starts before your eyes to basically disintegrate. Can you talk about that?
I haven't had that experience personally, but I've heard the same sort of thing, especially depending on changes in moisture, right? So I know of a site in central Texas, the Galt site, where they dig on a lot of, it's archaeological primarily. They're digging up, stone tools from ancient Native Americans. And some of the oldest components of the site date back to that Clovis period, or even earlier, potentially going back almost 20,000 years. They got some very early dates at that site. And I do know they have, I believe it was a mammoth but a proboscidean, one of the elephant relatives, that they found parts of at the site that they have chosen not to dig very much of, because apparently its consistency when you go to take it out of the ground is about like wet toilet paper.
Yeah.
So
I've
as
heard
you're
that
trying to
before,
dig
too,
that,
yeah.
it's completely crumbling right in front of you. Even with as much care as you're trying to take, it takes a lot of glue to try and very thin glue that you drip in there. We can call consolidant to try and strengthen it, to just try and save anything as you're digging it.
Stabilize a little bit.
To stabilize it. It's really kind of a nightmare scenario when it comes to digging fossils. So a lot of the time you kind of tend to avoid it if possible.
Yeah, let's let this cook for a little.
Right, you hope it continues to mineralize, and you hope it's
Right.
not actually demineralizing and dissolving under your feet,
know,
which is
let's
the
put
case probably of many animal remains.
Let's put a pin in this and circle back in a million years and see if it's a little more easier to work
It's easier
with.
to dig. Yeah.
So the timelines of fossilization, I've heard arguments made, examples given for, things can fossilize a lot quicker than over millions of years, which I want to ask you about that in a minute. But the example I've heard people give is, you go to hot springs and they put the wooden ladders down in the hot springs, and within months or just a few years, those are fully mineralized. Now, I looked into it, and it doesn't look like they are fully mineralized. They have a mineral crust
Building on the outside. Yeah.
but you cut through it, and it's still soft
in the
wood
middle.
in the middle. So that's not full fossilization. That is just the outside being crusted in all the minerals of the water. If you've ever been to hot springs anywhere in the world, they are super fascinating, very smelly, a lot of sulfur. You get used to it, a lot of rotten egg smell. But that's a lot of minerals coming out of the churning cauldron of the earth, and they attach to the porous material, the wood and everything. So you get mineral on there. I hesitate to call it rock because it's not technically. I've learned in geology it's not technically the same thing, but you get this mineralization, this crust on the outside of the wooden pole of the ladder, but it's not fully fossilized. Now, I want to get to petrified wood in a minute. We do want to talk about petrified wood. Can you speak to, I was talking to David Temple about this a few weeks ago. Mm-hmm. So you'll see news articles once in a while, and a recent one was, we found T-Rex soft tissue. Now, and that begs the questions, people, now can we pull the DNA out of it and da-da-da? Can we do a Jurassic Park situation or a dire wolf kind of thing, which no. I'll just say that right, no. But from my understanding, that we found T-Rex soft tissue, that's a bit of a misnomer, because it's not like you found
liquid blood,
a wet heart muscle. What did you find? Can you speak to that?
And I can't say I found it personally, right? These are other researchers out there, but what they found, what it appears to be is basically part of the blood, right? Something called heme, which is part of sort of the iron-bearing portions of the cells. So what they're finding isn't even like complete red blood cells, right?
Right.
What they're finding is basically chemical components that were once part of red blood cells, and it's been very badly degraded. It's been very badly broken down.
Right.
And so it's not something that you can. And there have been discussions of finding even other sorts of soft tissue remnants in dinosaurs, and even maybe tiny fragments of DNA. But the problem is that it's all just so badly degraded, so badly broken down, that being able to reconstruct anything from it is just, it's trying to build a mountain out of a sand grain, more or less.
Right, and I think you're hitting the nail on the head there, which is the headline makes you think that they found a wet, soppy, it's like a crime scene you just walked into and there's still blood everywhere. Yeah. Wet blood. That's not. That is, it's basically fossilized soft tissue, which is entirely different than soft tissue that you would find inside of me or you or any animal alive.
It's certainly not unreasonable to think that many of the elements, right, those most basic building blocks of the cells that make us might still be present in a lot of these fossils.
The iron in your blood.
From the blood could be left behind in
Traces
the rock formation, right? It's just the question of whether you can find anything that's recognizable as a structure.
Right.
And in this case, they found structures that more or less correspond to that part of blood.
Right. But you didn't find a wet blood spatter of a T-Rex?
Sadly, no. I mean, that would be
That'd
very
be amazing.
cool. That would be very interesting.
I keep trying to tell my wife, I say, if we can bring back dinosaurs, I want a pet T-Rex, like a 30-foot tall T-Rex in my backyard looking in through the upstairs
I'd be a little
window.
terrified. I'm
Yeah.
not going to lie. I probably wouldn't want to
She's-
be your next door neighbor.
No,
but,
she's not a fan of that. She's not a fan of that. And I whatever. So let's talk about petrified wood.
Sure. Mm-hmm.
Now, I will say the original question that started this podcast was technically,
Radioactivity.
can fossils be radioactive? And the answer is yes, fossils can be radioactive. We've already discussed all that. When I was walking around with this $25 Geiger counter, which in itself is apparently a miraculous thing, because not even apparently 20 years ago, Geiger counters used to be quite big
Outrageously
and
expensive.
and you can't. I went to Amazon. I was in the backseat of my minivan on the way home from Virginia. I was like, I'm going to order a Geiger counter.
For fun, why not?
Yeah, and it's going up right now, 0.19. It was at 0.10, now it's at the 0.19. We get these fluctuations every few minutes. We were talking off camera about, is this because we're near something radioactive, or is it because the solar winds are blasting particles?
Or is it
who knows?
because it's not a very expensive
Or is it
tool that's not very
$25?
sensitive, right?
Right, exactly.
It's also a possibility.
But I will say, when I was walking around the petrified wood on Tuesday, it went up 0.22. That in this area, and especially around the wood too, I was seeing spikes. 0.26. It's going up. We're still safe. It's still totally, but it is these little spikes. There was increased radioactivity around the petrified wood. Now, I stood there for a few more minutes, and it started to go back down again, which is why I was like, was it not? What's going on? But let's talk about petrified wood and mineralization of wood and radioactivity and all that stuff.
Yeah, so wood is one of those things that naturally as a living tissue, it does a lot of transporting liquid water essentially, but it's the sap of the tree, I suppose you would say, more than anything. So it's a naturally very porous thing, right? Again, in the local area, like I've been out on the rivers and seen wood that's in the river, and it's every bit as squishy as a sponge, and you could almost wring the water out of it.
Yeah.
And then you can see it, when the water levels drop and these point bars and things dry out, it shrinks and it leaves like a cavity around it where the sand holds its shape, and it has lost so much of its water weight and shrunk so much that it's completely changed its size and its shape, right? So these are very absorbent things. And if you have it in conditions where, again, there's lots of good minerals in the water, especially lots of silica, that silicon dioxide is the chemical formula for glass. So it's 2 silica, 1 oxygen. Or, one silica, 2 oxygen. You'll have to correct me there.
I'll put it on the screen, or I'll put it in those. This is a reminder of any podcast that we do here, audio, video, anything we do. If you're listening to this on Spotify or something like that, always check the podcast description, because I will put
we fact check ourselves.
The fact checks in there. So if you hear something and you think, that doesn't sound right, or you want to verify something that we've said, if there's something that needs more focus, like if I say the sky is blue, I'm not going to fact check something like that. But when it comes to molecules and is I know H2O is H2O, but just check the notes for any sort of clarifiers on things.
But in any case,
yes.
that free silica in the water, it's something that can be absorbed by wood, and when it does, it becomes well silicified. Basically, it becomes like glass. And the petrified wood that tends to survive is that has stuff that has undergone full replacement, more or less. That has been there really isn't any of the wood left. If there was, it would probably decompose. It wouldn't survive very well, and it's absorbed so much that essentially it's preserved the cellular structures sometimes. Other times it's undergone this replacement, and it's so changed that you can't really see those like structures, and it becomes a lot more ambiguous. But in certain conditions, it can do this full replacement and record what was there in the living structure so well that you can get incredible details.
Right.
But of course, it always depends on what minerals are present. So stuff that it forms very hard minerals tends to survive very well. So that's why silica is very good. But because they are so absorbent, they're going to want to, pick up pretty much any of those minerals that are present in that groundwater.
Right.
And so it is one of those sorts of fossils that might have a higher chance of being slightly more radioactive than others if there is a lot of those radioactive elements present.
Right.
So it's not out of the question that we might have some slightly higher spikes around some of our petrified wood, but again, always within safe levels that are
Right.
not at a danger to people. So
Right.
these are very, very low levels relative to what people think about when they think about radioactivity is usually power plants and nuclear
Chernobyl.
weapons where they have enriched these uranium ores or
Right.
those sorts of things where they purposely increase the amount of those radioactive particles relative to everything else. And that is where it really becomes very dangerous to life.
It's safe to say that if you eat a banana before you come to the museum, you've been exposed to magnitudes more radiation than anything you'll experience walking around a museum.
In our hall.
Or any general area unless you're going to the dentist or the doctor to get an X-ray, or you're being exposed to these exotic, wavelengths of radiation. That's not happening in the museum as we
With
sit.
fossils,
Now
yeah.
this is staying a little higher than, well, now it's back down to normal.
0.1, yeah, right
But
within normal
I am
ranges,
noticing
but yeah.
as we're talking that I am getting slightly higher than normal as we have been sitting near Dipsea. It has been spiking a bit higher. Maybe a radioactive particle just so happens to hit the sensor in here just right. But it's still, you're safe. You have to be exposed. I'm not a nuclear physicist. I'm not a nuclear technician. Don't take this.
Neither am I.
There's something like the elephant's foot or whatever in Chernobyl where you had that catastrophe and you have the molten whatever it is. I'm not going to say exactly what it is right now because I have to verify it. But it's very deadly, and you don't want to be around it for really even a split second, like even 1 second, because it's such an unguarded, at least at the time of the Chernobyl disaster, it was such a
concentrated source of radiation,
blast of radiation that there's very little survivability, and it's dying of a death involving radiation poisoning is horrible, but you have to be exposed to radiation either an insane level for a brief amount of time or a slightly elevated level for decades before you'd even maybe see a result of that radiation, of any sort of poisoning. You would have to eat so many bananas that you'd die of a burst gut.
You'd probably get more potassium poisoning or something than anything.
Exactly. The actual element itself might be what poisons you versus the radioactivity. You can die drinking water. You can drink too much water and be poisoned by water. But the point is, you're going to die by the poisoning of whatever element it is, because of the element it is, not because of the radioactivity messing with your cells and blowing apart your red and white blood cells. And it's you have to be exposed to a very high level of radiation, either over time or super high level instantly for it to be detrimental. You'll never experience that at the museum. I mean,
and actually, sort of another important part of this is radiation is that those radioactive elements are also key to how we date fossils,
right? Exactly.
As well, too, as we look at the formation of the rock and some of the radioactive elements in them, we can measure the parent-to-daughter isotope, right? Because of course, radioactivity involves these larger elements essentially decaying, right?
Right.
And it's those little particles that they're shooting off that are essentially the dangerous thing. And they're, for most of the levels are so low because there's such a small percentage that it's not anything that's going to be dangerous to the life that's living around these rocks normally, right? You got plants growing on top of them, you got animals walking around them all the time. But we can measure the change in the percentage of those essentially over such a long period of time, that we can get an idea of how long it's been since the rocks formed. So like uranium, thorium is one type of dating that's used for things that are more on the magnitude of hundreds of thousands of years. But
and that's the thing too. And then we're talking about scientific dating and specifically radiometric dating. There's all sorts of different ways to come up with data points to suggest how long something's been there, or how long it's been mineralizing, or how long it's been fossilized, whatever you want to call it. And so what we hear all the time, and we've touched on this in past podcasts, the radiometric dating method we hear from middle school is carbon dating.
Yep.
And we hear that once in 8th grade, and we don't take AP chemistry or anything after that to learn anything more. We hear carbon dating, and that's all we've known. That's all we've been told. That's all we understand to exist. But there are dozens of other radiometric dating methods, like you just mentioned, that isotopes between one bit of let's say iron and another piece of iron, it could be like 204 and 207. Like there's other methods for timescales. Carbon dating can be tough. It can be tainted or not as pure because of it's a very sensitive method to use, and it's accurate at its best out to a few thousand,
50,000 years,
50,000
more or
years.
less, right? Yeah. After that, it's very difficult to measure the amounts of surviving carbon-14. Yeah.
Exactly. So you wouldn't apply carbon dating to Dipsy's tibia here. It's way too old. So what would you apply to it?
You use a number of different elements depending on sort of what time frame you're looking at. Mostly it has to do with the length of the half-life, right? So for things like I said on the scale of hundreds of thousands, something like uranium thorium is a pretty common one. Going further back, I mean, there's potassium argon. I forget sort of what time scale that's used for, but I know some of the oldest ones are actually types of lead that have extraordinarily long half-lives, but will very slowly radioactively decay. And those are the sorts of elements they use to measure the age of the Earth, basically since the planet formed.
These windows, we estimate the age of the universe to be between like 14.3 and 14.7, somewhere in there. There's 200 million years on either side. That's the
confidence interval, the percent,
the margin of error, basically.
Yeah. Mm-hmm.
And you're like, 200 million years of a margin of error?
That's
huge.
just
quacky science. That's crazy. I did the math on this, and the 200 million year margin of error at 14.5 billion years is like a margin of error of 0.00 1%. It's 200 million years sounds like a whole lot, but at that time scale,
you're measuring such a big number.
Now you got to think about this. Now I attach it to my mind to an engineer and architect building a skyscraper.
Mm-hmm.
You cannot have massive margins of error when you're building a structure 1,500 feet tall. The margin of error at the base has to be the same margin of error within this tolerance that's insanely small to ensure that building
is actually straight up and down and doesn't fall over, and
Right. So for the universe to be this this old and have that narrow of a margin of error is like that makes sense. Why wouldn't it? If we're sitting here talking today, we're talking about radiometric dating. We're a species that we're getting a little heady here. We're self-aware, self-conscious to look at the stars and say, what are those?
How long have those been here? A lot longer than you or I, at least.
Exactly. And then if we have these materials on Earth, we make rockets and we send probes out there to figure out what all this stuff is. We build telescopes and Galileo looking at these things. Like, it's when you're talking about these time scales and these, the Earth could be 4.5 billion or 4.4 billion or 4.3, 4.5, 4.6. And matter of fact, when you do the radiometric dating, you get these data points that have this kind of margin of error of a few million years or 100 million years.
Yep.
But that is such a tight tolerance. The best engineers in the world making like car engines and the SpaceX rockets and things like that, they're probably operating within margins that aren't too far off, or maybe even a little sloppier than that margin of error of the universe. Well, the light turned off, so that might be a
good stopping point. Also, we've gone for nearly an hour at this point.
I know. I was like, Colin, can you have like 10 or 15 minutes, 10, 20 minutes? Well, Colin, the light died. That's our cue to wrap
Call it a day.
We'll do it again. So thank you so much for coming on the Beyond Bones podcast again.
My pleasure.
Cool.
Thank you so much for listening. Remember to check the podcast description for any corrections or extra goodies. I've been your mental curator, Johnny Hemberger. We can't wait to see you here at the Houston Museum of Natural Science. But until then, as always, stay safe and stay curious.